All right, question number 4 for our Friday quiz, May 21st, 2021. A horizontal glass tube closed at one end has a layer of dust laid inside it on its lower side. Sound is emitted from a loudspeaker that is placed near the open end of the tube. The frequency of the sound is varied, and at one frequency, a stationary wave is formed inside the tube so that the dust forms small heaps. The distance between 4 heaps of dust is 30 centimeters, and they've labeled that here. Labeled a loudspeaker are 30 centimeters between 1, 2, 3, 4 heaps of dust in a glass tube closed at one end. It's all checking out, right? The speed of sound in the tube is 330 meters per second. Okay. We want to determine the frequency of the sound emitted by the loudspeaker. What is the frequency of the sound emitted by the loudspeaker? If you're given velocity and you're asked to solve for frequency, sometimes that could be the way that you start to sort of, think through it. You say, well, why did they tell me the speed? Velocity of a wave is wavelength times frequency. The fact that they give you this value and they ask you to solve for frequency, that right there kind of roadmaps your path to the solution. You say, I must determine the wavelength, because if I knew the wavelength, that's the missing thing to solve for the frequency, right, using this equation. So then we can kind of look up here and say, okay, I should be able to figure out the wavelength from this figure. So why would the dust sort of settle in these heaps here? Because the air, the loudspeaker, has this sort of coil and then a paper cone, and that paper cone is pushing air, right? And the air particles move parallel to the direction of energy transfer. So the speaker initially pushed particles sort of this way, and they vibrate left and right at some frequency, this many times per second, either 1650 or 2200. So lots of times per second, these particles are moving backwards and forwards. Once it gets here, there's obviously a node here. The particles can't move through the glass tube, and that's why you see sort of there's a heap right there. So that's a node. So we're saying like all the nodes right here are the areas of no displacement where the heaps sort of pile up. The antinodes would be here. Here's where the air is moving the most, sort of clearing out all of the dust that would sort of be there. And so we can kind of see the antinodes here. Remember, we draw this with loops. It's kind of like, okay, there's a loop right there. There's a loop right there. Loop right there, right? So we have all these sort of loops that go node to antinode down to node, kind of like that. And there's the complete sort of waveform, the standing wave. And now what we need to do is look at, okay, we know between 4 heaps is 30 centimeters. I like to think about it like this. There is one wave, right? So sort of you can visualize an entire wave to there, and then you got to go another half a wave. So we go 1.5 waves between these. We could say more generally that the distance between 2 adjacent nodes is half a wavelength. So that's kind of useful to just have as a studyable statement in your notes. The distance between adjacent nodes on a stationary wave is half a wavelength. Okay. For this one, I prefer to say 1.5 waves is 30 centimeters. I like to just sort of translate what I can visualize into a mathematical equation that's perfectly solvable. And so if that makes sense to you, that there is 1.5 waves, right? We can see 1.5 waves is 30 centimeters. 1.5 waves is 30 centimeters. Divide each side by 1.5. We've got the wavelength now. 30 centimeters divided by 1.5. That gives us 20 centimeters. That is 0.2 meters, right? 20 times 10 to the negative 2, or 0.2 meters. And so now we've got the frequency equal to the velocity divided by the wavelength. We've got the velocity of 330. We've got the wavelength of 0.2. And so this is in meters per second. This is in meters. And so we get the frequency in reciprocal seconds or hertz. 330 divided by 0.2 equals 1,650 hertz. Choice A for question 4.